Welcome to another lesson of Transparent Physics, and in today's lesson we're going to be focusing on the first two-thirds of Newton's three laws of motion. So that's going to be the first law and the second law. The goals of today's lesson are going to include describing, of course, Newton's first and second laws of motion. In the process of doing so, you're also going to get a definition of inertia, and we're going to introduce probably one of the most important equations in your first year physics course, F net equals ma. Before we get into the laws themselves, let's put them in a little bit of context. Isaac Newton summarized these laws of motion, and again, not exactly in the way that we're going to talk about them. His phrasings were a little bit different, but at heart, these were the arguments that he was making. And he published several volumes in 1687, known in shorthand as the Principia. And fun side trivia fact, he published these at the urging of his colleague Edmund Halley, and Halley you may know from Halley's Comet fame. Now, these books contained lots of very, very important ideas about mechanics and planetary motions, and not all these ideas Newton came up with on his own. He was aware of the literature at the time. He absorbed a lot of ideas and then added his own insight into them. And his work helped establish what we now know as the field of mechanics as a quantitative science. And the laws of motion that he put forth established a framework in a pretty simple and concise set of laws to explain a wide variety of scenarios. And as you study science, if you can take a small statement or series of statements and apply them to an extremely broad range of scenarios, that is the hallmark of a powerful scientific idea. At this moment, you might be asking yourself, Transparent Physics, why are we only talking about the first two laws in this video? All three laws of motion at once is a lot to take in, and it would make for a long video. So we're going to split it up. The first two laws fit together nicely because they both deal with forces and acceleration, just from different sides of the same coin. And the third law will get its own video because that is a very different conversation. Okay, when we're talking about the laws of motion, there's usually a couple different ways to phrase the same law. That's fine. They just come at it from different perspectives. I'll try to give you a couple different perspectives, and you just pick the one that works best for you. A pretty concise way of looking at Newton's first law of motion is to say when balanced forces act on an object, its motion won't change. Remembering from an earlier video, balanced forces exist when the forces acting in opposite directions cancel each other out. Maybe it's a tug of war where nobody's winning. Maybe it's an object just sitting at rest on a surface. You can have forces acting to the left, forces acting to the right, but when you add up the magnitudes each way, the sum is zero. Deeper flashback all the way into kinematics. When we're talking about the change in motion of an object, that is acceleration. So anytime we're talking about change in motion, we are simultaneously discussing acceleration. So we can rephrase the when balanced forces act on an object, its motion won't change as an object won't accelerate while the forces are balanced. Or more literally, when balanced forces act on an object, it won't accelerate. Same idea, just a different set of sentences, although acceleration really is the focus as far as the first and second laws go. As I mentioned, there's different ways to look at the laws. A sort of classic introductory approach to Newton's first law is to say an object in motion will stay in motion and an object at rest will stay at rest. And if you think the formatting looks a little weird on the screen right now, that is because this isn't really the way that I like to say the phrase. If we're going to use this phrase, that's fine, but let's trick it out a little bit to make it a little more precise and say it like this instead. An object in motion will stay in motion with a constant velocity, and an object at rest will stay at rest while balanced forces act on it. So we're specifying that the motion is a constant velocity, and then whether it's in motion or at rest, we do add in that phrase balanced forces, because balanced forces is key to understanding when this is going to apply. This idea of an object maintaining the motion that it has is also known as inertia. And inertia is a concept in introductory physics. And if you look inside the word inertia, you see the word inert. Inert has a bunch of different definitions, but they're usually circling somewhere around the idea of not changing or not reacting. And when we look at it in the context of physics, what is inert is the velocity. It means the velocity is not changing. Be cautious how you interpret that. That doesn't mean the velocity is zero. You can have a non-zero velocity that is not changing, and we'll show you some examples of that idea. Newton's first law, therefore, is sometimes known as the nickname the law of inertia, because it talks about how the motion of an object is going to keep doing what it was doing. As a side note, it's easy sometimes when you're learning science and you look at a textbook or listen to a lecture, and it's easy to imagine, well, that's the way just things have always been, that's what we've always thought. But in many cases, in many fields, our current theories and ideas aren't the same as they were decades ago or centuries ago. There had to be some sort of intellectual battle between older ideas and newer ideas, and as long as we look at things logically and critically, we can work our way to better theories and laws over time. And Newton's takes on motion did challenge some long-held beliefs. If we go all the way back to ancient Greece and Aristotle, objects were assumed to have what was called a natural state of rest. That means everything pretty much wanted to be at rest, and if it wasn't at rest, that was sort of a temporary thing, and that would correct itself over time. And casual observations support this. Things aren't just generally moving around on their own. If they are moving, it's probably because there's energy in them from maybe animals eating food or me throwing something. And again, it doesn't necessarily seem wrong to say, unless there's some sort of help, things are going to be at rest. The ideas behind that are more than we're going to get into in this video, but basically in Aristotelian thinking back in the day, like everything was made up of elements: earth, air, fire, water. I mean, everything was made up of elements, even things that don't obviously look like they are on fire or something like that. And that elemental composition comes with certain properties and characteristics, including the idea of how it would tend to move. So you've got that as a background, and then we can override that through sort of temporary violent disturbances. The idea is, it doesn't matter what a pineapple is made of in terms of its elements. I can pick it up, I can throw it, I can force it to move, but that movement is temporary because that's an unnatural disturbance of its natural state. Drilling deeper into those ideas, there's challenges. They're not flawless theories. But Newton comes in and replaces these thoughts, these pseudo-scientific explanations, with a precise framework that relies on measurable conditions to determine how things are going to move. And again, while I'm giving Newton the credit here, he wasn't working in a vacuum. Other people had some of these same ideas, although Newton was straight out flat a scientific genius and had a way of looking at a lot of disparate elements and pulling them together and deciding, what was the essential ideas of what he was looking at. And he wasn't a bad experimentalist on his own either. Okay, we're probably around halfway through the lesson at this point. Might be a good time to pause and hydrate with a little bit of tea. That's good. Okay, so examples of Newton's first law. And remember, since Newton's first law involves balance forces, these should all be examples of balance forces as well. So the first example is a capybara lying on the ground. It is obviously an object at rest that stays at rest. You've got a force acting up on it from the ground. The dirt that it's sitting on is pushing up on him or her. And at the same time, gravity is pulling down on the capybara. So these forces are balance forces. Nobody's winning, so the capybara is not accelerating in any particular direction. The next one is a classic Newton's first law trick, the old pull the tablecloth out from under the stuff on the table trick. I'm sure it maybe has a more elegant name than that. This one I pulled because I have seen many examples of somebody pulling a tablecloth out from under stuff in a table, but I have never seen an example where somebody then uses that same tablecloth and puts it under something else. Now this is a bit of a we're cheating a little bit usually with these examples. If you take a close look at the objects on the table, they do move a little bit. The argument is, though, that as long as the tablecloth is smooth enough and it's pulled quickly enough and you've got the right things on the table, that the friction between the tablecloth and the items is so small that it doesn't have a chance to really accelerate the object at all. So we'll be forgiven for the fact that these things do move slightly. But you definitely can see the argument is that an object at rest stays at rest. So at the bottom here, I just have a single dot by itself, the idea being that we're not really looking at any unbalanced forces of interest. Obviously, there's a force up and a force down from the table and gravity, but we're just going to wink a little bit and pretend there's no forces at all in the horizontal direction. And the last one is a dog that is in motion and stays in motion. So in this case, the dog started running sometime before the video, and when the little GIF starts up, the dog is in motion already. It stops moving its legs. Obviously, it's not trying to propel itself forward anymore, but it is in motion and it stays in motion. And again, I have just sort of an empty dot there. The idea is there's no unbalanced forces of interest. Again, we could note that there is a force acting up on it from the ice and a force acting down on it from gravity, but at this point it would be the horizontal forces that are important, and we can just assume there's no horizontal forces. The dog is in motion, and staying in motion is free. We don't need to exert a force to keep it moving once it already is in motion. Okay, time to turn the page and start taking a look at Newton's second law. We'll look at a verbal definition of it first. There's lots of ways to phrase it, just like the first law. My go-to way to phrase it would be say an object will accelerate in the direction of an unbalanced net force. And at first blush, that maybe sounds a little redundant to say unbalanced and net force. Let's first review what the idea of a net force is. Net force means the sum of the forces. Think like food packaging when it says net weight. That is the weight of the food and the packaging itself. So when I say in the direction of an unbalanced net force means we're taking a look at all the forces of interest and we're seeing whether or not they're unbalanced. You could technically have a net force of 0, but that's still a net force, but that would be balanced forces. So I try to specify that we are looking at unbalanced forces. And when we are trying to figure out the sum of the forces, we are looking in terms of either vertical or horizontal. We're adding all the forces to the left and the right and seeing what they add to. Or we're adding all the forces up and down and seeing what they add to. The sum of those forces in either direction is going to tell us whether or not the object is accelerating according to Newton's second law. Hence, Newton's second law is sometimes referred to as the law of acceleration. Switching to the math side of things, for Newton's second law, who shows up to start with? Our vector notations. That means that we're probably going to have some terms in the formula that are vectors, but we don't need you guys yet. Why don't you guys, get out of here. We'll take a look at you guys later. The equation F net equals MA is not actually that complicated for as important a role it plays in introductory physics. F net refers to net force, M is for mass, A is for acceleration, and depending on your teacher and the notation they use, you may see the term F net replaced instead by a sigma F. Sigma just means summation, so either way you're fine, same formula. And when we are looking at this as a formula, force is a vector quantity, acceleration is a vector quantity. So if you're at a slightly higher level course, probably you will include the vector notation over the formulas. I won't be very concerned about doing that in this particular course, but I do like to point it out right now because it's good to note that the direction of the force and the direction of the acceleration is the same direction. Whatever direction the net force is, wherever the unbalanced force is winning, Newton's second law tells us you'll accelerate in that direction. So it's just a way to mathematically quantify it. And you're going to get a lot of equations in your introductory physics course, but I would say this easily could be on the ballot for the most important equation that you're going to get this year. It has an extremely broad application, and at least an introductory course that focuses on mechanics, this is going to be a very, very widely used formula. If we want to dig a little deeper into that formula, we can manipulate it a little bit and get a bit more insight as to the acceleration depending on the circumstances, because that's really what Newton's second law is all about. So we're going to solve F net equals ma for the acceleration. That means we'll divide mass out on both sides. So we'll be left with the formulation acceleration equals F net over mass. And when we analyze the formula a little bit, we see that the acceleration is impacted by two factors, one in the numerator and one in the denominator. So as the net force increases, you're going to see an increase in the acceleration, which makes sense. The more the force is winning, the more acceleration you should expect to see. But one thing that hasn't really come up in the discussions yet is the impact of the mass. The mass, as the mass gets larger, the acceleration is going to decrease. So a heavier mass is harder to accelerate. Put those two things together, larger net force creates a larger acceleration, a larger mass creates a smaller acceleration. Get those two things working in concert, and you've got yourself a Newton's second law. For some examples of Newton's second law, I found for your viewing pleasure a extraordinarily physics-packed GIF/GIF, and there's many aspects of this that we could study. We're just going to focus on a couple for space constraints here, but we can take a look at the dad hitting the smaller raft. He jumps off the larger platform and hits the smaller raft. As he hits the smaller raft, he slows down. That's an acceleration. Anytime there's an acceleration, there needs to be an unbalanced force combination associated with that, or at least one unbalanced force. And so we can take a look. The dad has a force acting up on him by the raft. The dad has a force acting down on him by gravity, but you can see I did not draw those arrows the same length. The force up on the dad is larger than the force down on the dad. So therefore, there's a net unbalanced force acting upwards, and so that's the acceleration on the dad. We mentioned in an earlier lesson that when the acceleration acts in a different direction than the velocity, that means you're going to slow down. So the dad is moving downward when he impacts the raft, but he has an upward net force, upward acceleration. So he's going to slow down. So as he hits the raft, he comes to a stop. We can take a look then at the other side of the raft with the child getting launched from the raft. Now here, the child starts at rest. In the first example, the dad started in motion. Newton's laws don't really care whether you're in motion or at rest. As far as the forces go, the impact of those forces is going to be the same regardless, whether it's an unbalanced or balanced force. That will determine what happens to your velocity, not inherently the velocity you begin with at that moment. We're going to assume that there is a larger force acting up on the child than acting down on the child, based on the fact that the child accelerates upwards. I don't know that it would be exactly the same as the force acting up on the dad, but it's going to be what it's going to be. I will say that the force acting down on the child is going to be lower than the force acting down on the dad, because gravity is going to pull less on the child because the child has a smaller mass. But the child definitely does have an upward unbalanced force acting on him or her, and the acceleration is pretty healthy. You can see the child goes up a lot higher than the dad did. That could be a combination because the net force acting on the child is larger, maybe. Also, the child's mass is smaller. Remember, smaller masses are easier to accelerate. So the child maybe gets more oomph out of the same magnitude unbalanced force just because they are less mass. And the last one we can focus on is just as the child's flying through the air. We're going to ignore air resistance, so the only force acting on the child is gravity, but that's enough to cause an unbalanced force. As the child's moving upward, if there's an unbalanced force acting down on the child, that means the kid's going to slow down. And again, if you watch, the kid slows down as they go up into the air. And then as they fall downward after reaching the peak, the force is still acting downward, the acceleration is still acting downward, but now since force and velocity, well, acceleration and velocity are in the same direction, the child speeds up. So the child slows down on the way up, speeds up on the way down, but that's all Newton's second law. And again, we could talk about the dad as he drops off the platform. We can talk about the kid as they hit the water. I mean, there's so many examples of Newton's second law here, but I think we covered it pretty effectively there. And that is our summary of the first and second laws of motion. And when I was a kid, newscasts would sometimes end with, I don't know, like the editor-in-chief or something coming on and giving a sort of an opinion editorial at the end of it, not to be considered actual news, but just sort of color commentary. So I'm gonna do that today. And my argument here is going to be that if we had to let go of one of Newton's laws of motion, we could probably do without the first law. Here's my logic. Net force is the sum of the forces. If net force is equal to 0 newtons, and again, net force would be equal to 0 newtons if the forces are balanced. That's the purview of the first law of motion. Take a looking at the second law. Acceleration is F net divided by mass. If F net is equal to 0 because the forces are balanced, it doesn't really matter what the mass is. 0 divided by anything is going to equal 0 as long as it's some mass at all. And that is what Newton's first law tells us. When we take a look at Newton's second law, under a circumstance when forces are balanced, aka net force is equal to 0, it tells us that there's no acceleration. And we started off this video by saying that exact same thing. When the forces are balanced, the object's not going to accelerate. It's either going to stay at rest or it's going to keep moving with a constant velocity. So there it is. That's my take on the argument that Newton's first law is really just a special case of Newton's second law. I'll let you chew on that for a while. All right, we're at the end of the lesson. So as always, if you found the content useful, consider liking the video. If you have any questions about what was covered, leave a note in the comments section. And if you want to see more videos of introductory physics, please consider subscribing to the channel as well. Thanks for watching, and I hope I've made things a little clearer for you on this lesson of transparent physics.